In this video, we're going to be talking about limits at infinity and horizontal asymptotes. In this section, we want to explore what happens when we plug in very large input values into functions. You should have explored the topic of end behavior of a function in a pre-calculus course. Limits at infinity go hand in hand with end behavior of functions. Example 1 says, describe the end behavior of the function p of x equals, and then we're given this polynomial. Now you might remember from pre-calculus, when you're talking about the end behavior of a polynomial, really you only care about the leading term. And the leading term is the term that has the highest power or the degree. And in this case, the leading term is negative 9x to the 7th power, which means that these terms we don't really care about. And then the thing that's going to affect the end behavior are two things. We care about the degree as well as the sign of the leading coefficient. In this case, our degree is 7, which is odd, and then the sign of our leading coefficient is negative. And so when we're talking about end behavior, we're really talking about the limit as x approaches infinity of our function here. And because the degree is odd and the leading coefficient is negative, we can kind of use something like y equals negative x cubed as a template. And so y equals x cubed normally looks something like that, but because we have the negative, it's reflected, so it would look something like that. And we can see as we plug in really large positive values into negative 9x to the 7th or into negative x cubed, we get really large negative values, meaning that this is going to go off to negative infinity. And then we have the limit as x approaches negative infinity of our polynomial p of x, and we can see that that is going to go off to positive infinity. So previously we had a little bit of a different notation for end behavior, but in this case, now that we have the idea of limits, because we're in calculus, we can describe the end behavior in this fashion. And here I just wanted to quickly review and highlight the 4 cases when you're talking about the end behavior of a polynomial. So this is review from pre-calculus. Let's go back to talking about limits now. Example 2 says fill out the tables below using the function t of x equals 3x squared over x squared plus 1. Now I just want to highlight that this is a rational function. And I'm going to use a calculator to fill in this table. Now you'll notice that the output values in both of these columns happen to be the same, whether we are plugging a negative or a positive value. So this row for negative 10 and positive 10, those are the same. And I just want to highlight that this is because t of x is an even function. And a function is even if for all x values in the domain, f of negative x is equal to f of positive x. And the way that that manifests in a graph is that if you reflect the graph over the y-axis, it returns the same graph. So a very basic example of this is the even function y equals x squared. Here's the y-axis, here's the x-axis. If I were to take this and reflect it over the y-axis, it would give me the exact same graph. All right, so let's kind of observe what's happening here. These values in the very first column, these x values are approaching negative infinity. And as you can see, these values are approaching 3. These values are approaching positive infinity, and then these values are also approaching 3. And so what this means is that we have the limit as x approaches negative infinity of our t of x function is equal to 3, which is also equal to the limit as x approaches positive infinity of our function t of x. And so it turns out that in pre-calculus, we learned that this rational function has a horizontal asymptote. at y equals 3, at the line y equals 3. And this is kind of why, because as we take the limit as x approaches infinity, and as x approaches negative infinity, the output values approach the value 3. So let's talk a little bit more about horizontal asymptotes. We can see here that the function value approaches a finite number as x got extremely large or extremely small. This type of behavior describes a horizontal asymptote. So, definition, the line y equals capital L is called a horizontal asymptote of the curve y equals f of x if either the limit as x approaches infinity of f of x is equal to capital L, or the limit as x approaches negative infinity of f of x is equal to capital L. Here's another definition. Let f be a function defined on some interval from a to infinity, then the limit as x approaches infinity of f of x equals capital L means that the values of f of x can be made arbitrarily close to capital L by taking sufficiently large x values and plugging them into f of x. Example 3 says find the requested limits using the given graph of the function f of x. So we have this interesting looking piecewise function here, and I kind of just want to highlight here there's a little arrowhead, meaning that it's going to continue on to the right, and it will continue on in this fashion. So I just want to emphasize that this does not mean that this is going to go down forever like that. What it does mean is it will continue on kind of in this fashion where it gets smaller and smaller and smaller towards this horizontal asymptote there. Okay, so now that we got that out of the way, let's go ahead and compute these limits. Part A says we want to take the limit as x approaches infinity. So like I said before, this is going to get smaller and smaller and smaller and kind of look something like that and go on forever. And so if I were using the balloon analogy, we can see that the y value that it's approaching is positive 10. And then similarly, as x approaches negative infinity, that means that we're here, it's kind of going like that, and it's kind of just oscillating and getting smaller and smaller, and that is approaching negative 8. In part C, we have the limit as x approaches negative 3 from the right-hand side. So here's negative 3, and we're approaching from the right, and so we can see here that these y values are going down, and so this would equal negative infinity. If I were approaching negative 3 from the left, here I'm using my little balloon person. There's the balloon. They're getting closer and closer to negative 3 from the left-hand side, and the balloon is approaching this location right here. We can see that that has a y value of 10, so this is going to be 10. In the next part, we're taking the limit as x approaches 3 from the right-hand side, and so that's going to be right here. If I were using the balloon person analogy, they're getting closer and closer to 3 from the right, and the balloon keeps going down, so that is going to equal negative infinity. And then as x approaches 6, this is an overall limit, and so notice that as we approach from the left and as we approach from the right, both of these are going off to infinity. So this one will equal infinity. And that's it for example 3 here. Example 4 says, using your knowledge of the graphs of the following functions, evaluate each limit. So I'm going to go ahead and graph each of these before we start to evaluate these limits. The first function is f of x equals 1 over x. That looks something like this. It's going to be in quadrants 1 and 3. And the next function, g of x equals 1 over x squared. Since our numerator is a constant and our denominator is x squared, that means that g of x will always be positive. If it's always positive, that means that it can only exist in quadrants 1 and 2 because the y values are always going to be positive. So if you were to graph this function, it looks something like this. And then the last graph, we have h of x equals arctangent of x. I just want to emphasize, remember that this is the same thing as tangent inverse of x. And so one way that you could think about the graph of this is if we graphed the regular tangent function. So y equals tangent of x. We know that that has vertical asymptotes at pi over 2 and negative pi over 2. And so its graph looks something like that. And remember, when you graph an inverse function, we reflect it over the line y equals x. And so for the graph of arctangent, we're going to have a horizontal asymptote here, and this is y equals pi over 2. And then we're going to have another horizontal asymptote here, and this is at y equals negative pi over 2. So if I fill in the graph, it looks something like this. All right, let's go through and evaluate these limits now. I'm going to give you a chance to pause the video because I'm going to go ahead and go through these kind of quickly. So the limit as x approaches infinity of f of x, that is equal to 0. As x approaches negative infinity, that limit is also equal to 0. And then if we're approaching 0, this overall limit, that means we're approaching 0 from the left, from the right and from the left. Notice that these are going, one's going to infinity and the other is going to negative infinity. So because they're going to different places, this limit does not exist. All right, the limit as x approaches infinity of g of x, that's going to equal 0. As x approaches negative infinity, this is also going to equal 0. Then as x approaches 0, we're approaching from the left and from the right. Notice that both of these are going off to infinity, and so this would equal infinity here. Now, the limit as x approaches infinity of h of x. So if I were using the balloon analogy, I have my little balloon person here. If they're approaching infinity, that means that they're walking to the right forever, and you can see that the balloon is going higher and higher and higher, but it's kind of being capped at this horizontal asymptote, and the location of that horizontal asymptote is pi over 2. As I approach negative infinity, it's going down towards negative pi over 2, and then as we approach 0, the balloon would approach the origin, which has a y value of 0. So that concludes example 4. This next theorem says if r is some positive rational number and c is any real number, then the limit as x approaches infinity of c over x to the r power is equal to 0. And similarly, the limit as x approaches negative infinity of c over x to the r power is also equal to 0. And we actually saw some cases of this, right? So if I come back here, in both parts above here, we have this function, So f of x here is a constant over a positive power of x, and then g of x is also a constant over some positive power of x. And notice that all of these limits are 0. And when you have a constant divided by some really, really large number, if x is going to infinity, then it's going to get infinitely small, and again, it will go off to 0. So this is just an illustration of this theorem that we have. In cases that we need to get the form, the limit as x approaches infinity of c over x to the r power equals 0, we can accomplish this by multiplying the numerator and denominator by 1 over x to the power of n, where n is the highest power of the denominator. What exactly does that mean? Well, let's put this into practice in example 5, which wants us to evaluate these limits here. In part A, we have the limit as x approaches infinity of this rational function, and we want to multiply the numerator and the denominator by 1 over x to the power of n, where n is the highest power of the denominator. So in part A, the highest power of the denominator is 3. So if I'm following this, what I'm going to do is I'm going to multiply the numerator by 1 over x cubed, and I'm also going to multiply the denominator by 1 over x cubed. And remember, I can multiply a function by 1, and that will not change the function itself. And 1 over x cubed divided by 1 over x cubed is a fancy form of the number 1. So we're not changing the actual function, we're just changing what the function looks like. So I have the limit as x approaches infinity. I'm going to take 1 over x cubed and I'm going to distribute it to every term in my numerator. And so if I multiply 4x cubed times 1 over x cubed, let me write this out. So I have 4x cubed times 1 over x cubed. What's going to happen is these will divide out and I will be left with 4. And then I have plus 2x times 1 over x cubed. This will simplify to 2x over x cubed, which is the same thing. We can divide out the x's, and that will be 2 over x squared. So I'm going to go ahead and clean this up, and I'm also going to distribute the 1 over x cubed to the last term as well. All right, so I'm at this stage, and you might remember from an earlier section when we learned about limit laws, I'm taking the limit of a function that has a numerator and a denominator, and there's one of the limit laws that would allow me to apply the limit to the numerator and the denominator. What I mean by that is I could rewrite this as the limit as x approaches infinity of the entire numerator. And then I could also apply it to the denominator. And there's another limit law that says if you're taking the limit of a sum, you can apply the limit to each of the terms in the sum. So essentially, I'm just taking the limit of the numerator and the denominator. And based off this theorem that we had here, we can see that all of these fractions, for example, 2 over x squared, as x goes off to infinity, this fraction goes off to 0, as well as this one. This will also go off to 0. This goes to 0 as well, and then this also goes to 0. So if I'm kind of thinking about what happens as x gets larger and larger, this is equal to 4 plus 0 minus 0 over 8 plus 0 plus 0. Now, if you're one of my calculus students, I want to emphasize that we're not using direct substitution here, because the way that direct substitution works is if we're taking the limit as x approaches a number, we're able to plug that number into the function. In other words, remember that direct substitution is the limit as x approaches a of f of x. Direct substitution is when you evaluate the function at that x value that we're approaching. However, in this case, infinity is not a number. Infinity is not a number. And so we can't plug in infinity into, for example, 2 over x squared. How do you square infinity and then do 2 divided by that number? That's not really what's happening. We're not plugging infinity into a fraction or into a function. We cannot evaluate that because infinity is not a number. However, what we're doing is we're examining what happens as x gets extremely large. So again, I just wanted to highlight that this is not an example of direct substitution. And so notice that I don't put capital D, capital S over the equal sign in this instance. So now we have 4 over 8, and that simplifies to 1/2. And we would have expected that to be our answer if we kind of use the ideas behind pre-calculus, because our rational function, the numerator and the denominator have the same degree. And so in pre-calculus, you would have learned that the horizontal asymptote is the ratio of the leading coefficients, which in this case would be 4 over 8, which simplifies to 1/2. So that concludes part A. Let's move on to part B, which tends to be a more challenging limit for calculus students. So let's talk about it. All right, we have the limit as x approaches negative infinity of the function x plus the square root of x squared plus 2x. And the strategy that I'm going to take on is I'm going to once again multiply this by a fancy form of the number 1, and I'm going to multiply the numerator and the denominator by the radical conjugate. So remember, the radical conjugate is x. In this case, it'd be x minus the square root of x squared plus 2x. All right, so I want to multiply out the numerator, and you can do that in several different ways. You could FOIL. I'm going to use the box method. So we have x, and we have here the square root of x squared plus 2x. Here I have x, and then negative square root of x squared plus 2x. In my first box, x times x is x squared. Here I'm going to have x times the square root of x squared plus 2x. Here I will have negative x times the square root of x squared plus 2x. And then in the last box, I would have negative, and multiplying those two values together would get rid of the square root. Okay, so one of the many reasons I like the box method is if there are like terms and you line it up vertically and horizontally in descending order of powers, then the like terms will usually end up in the diagonals. And so notice that if I added those two diagonal terms together, their sum would be 0. Now I have x squared. I'm going to distribute the negative sign in the last box. So I have x squared minus 2x, and these result in a sum of 0, so I just have negative 2x left over. Coming back over here, we have the limit as x approaches negative infinity. I've simplified the numerator, and it simplifies to negative 2x. And the denominator, I'm just going to copy it down because 1 times this thing gives us x minus the square root of x squared plus 2x. All right, so where do we go from here? Well, in the radicand, I would like to factor out an x squared. Let's see what this looks like. So I have the limit as x approaches negative infinity. In my denominator, I'm going to factor out x squared from both of those terms. So if I factor out x squared, that's going to leave me with 1 plus 2 over x. And you might be asking, why are we factoring out x squared instead of x? Because x is the greatest common factor in the radicand. And the reason that we're factoring out x squared is because we want to use the square root property that says the square root of a times b is equal to the square root of a times the square root of b. So I'm going to split this up into two different square roots. Now we have the limit as x approaches negative infinity of negative 2x over x minus the square root of x squared times the square root of 1 plus 2 over x. Now, I'm going to replace the square root of x squared. In pre-calculus, you would have learned that the square root of x squared is equal to the absolute value of x. Now, also in pre-calculus, you should have learned that the the absolute value of x is a piecewise function, and it's equal to x if x is greater than or equal to 0, and it's equal to negative x if x is less than 0. Now, because we are taking the limit as x approaches negative infinity, that means that all the x values that we are examining are less than 0, which means that I can replace the absolute value of x with negative x. And again, this is the part that students will often get thrown off by, or one of the parts in this question. I think that there are multiple places where students will get tripped up. But here, the absolute value of x, we are going to replace it with negative x, again, because the x values that we're thinking about, they're all negative. So this would turn into x minus negative x times the square root of 1 plus 2 over x. Now, I can simplify this. X minus negative x, that is the same thing as x plus x. Now what I can do is I can factor out an x from the numerator. Now, I want to caution students because a common thing that I will see students do in this step is they'll say, oh, x plus x, so that gives me 2x, and then the square root of 1 plus 2 over x. It does not work like that. We can't do that because of the square root portion, but both of those terms do have an x, and so I can factor out an x. So I have the limit as x approaches negative infinity. If I factor out x, I would be left with 1 plus 1 times the square root of 1 plus 2 over x. Notice that I didn't write that second one. You can if you'd want to. And then now what happens is I have this x and this x, they will divide out. And we can now kind of start to evaluate the limit because of those x's being gone. All right, so using that theorem that we saw from before, if I'm taking the limit as x approaches negative infinity, what is happening to this fraction? Well, according to that theorem from earlier, that fraction is going to go off to 0. So this is equal to, and again, we're not using direct substitution because our x is approaching negative infinity instead of some number. So I have negative 2 over 1 plus the square root of 1 plus 0. And if I were to simplify this, we finally get our answer, or our limit is equal to negative 1. All right, so in part C, we have the limit as x approaches infinity of 2x cubed plus 5 over 3x squared plus 1. I'm going to use that strategy that we saw in the purple box earlier, where I want to multiply by 1 over, and then the power of x is the highest power in the denominator, which in this case is x squared. So now I'm going to multiply 1 over x squared and distribute it to each of these terms. In the numerator, if we do that, we get the limit as x approaches infinity of, let's see, 2 over x plus, no, that's not right. That would be 2 times x, because the numerator has the higher power, so it'd be 2x plus 5 over x squared over 3 plus 1 over x squared. Okay, so what's happening as x gets larger and larger? Well, this is going to go off to 0. This is going to go off to 0. And we're essentially left with 2x over 3. But as x gets larger and larger, the numerator is going to continue to increase. And so we know that this is going to go off to infinity. And again, from pre-calculus, we would have expected that because the degree of the numerator is higher than the degree of the denominator, meaning that there is no horizontal asymptote. And so we would expect that the limit would go off to either positive infinity or negative infinity. Example 6 wants us to evaluate the following limits. In part A, we have the limit as t approaches infinity of the square root of 3 over 7 plus the natural log of t squared plus 1 all over t squared. So I'm going to use one of my limit laws, and I'm going to split this up into two different limits. So I have the limit as t approaches infinity of root 3 over 7 plus the limit as t approaches infinity of the natural log of t squared plus 1 over t squared. Now, there's a theorem that we learned in the previous section that talks about when we're taking the limit of a continuous function, and the natural log, that is a continuous function on its domain. And so that theorem, what it allows us to do is it allows us to rewrite this as the natural log of the limit as t approaches infinity of t squared plus 1 over t squared. And that becomes a lot easier because now we're taking the limit as t approaches infinity of this rational function. And because the degree of the numerator and the denominator are the same, we would take the ratio of the leading coefficients. And so this then is equal to the natural log of, as we take the limit as t approaches infinity, we take the ratio of the leading coefficients, and 1 divided by 1 is 1. And then we have that the natural log of 1 is equal to 0. Now, we can take the limit as t approaches infinity of this thing. This is a constant, and so the limit would just equal the square root of 3 over 7. And so our final answer is the square root of 3 over 7 plus 0, which is just this. And so that's our answer for part A. For part B, I am once again going to split the limit into two using my limit laws. All right, so the first limit, as theta approaches infinity, the numerator is a constant, so we have that theorem. We know that this is going to go off to 0. And then we saw earlier that the limit as theta approaches infinity of arctangent is equal to pi over 2. So I'm just going to copy that over. So we have 0 minus pi over 2. So our final answer in this case would be negative pi over 2. All right, so that concludes this video on limits at infinity and horizontal asymptotes. Thanks for watching.